I just took some current technology and built some devices that possibly should have been built a long time ago. A, B, C.
The first step
D,
is to train the glove
E,
to understand Nancy's
F,
style of fingerspelling, literally her handwriting.
H, I.
Each bar on the screen shows the voltage from each of the 14 sensors for every letter she shapes.
N.
These patterns are then stored in the computer's memory. The glove is also hooked up to Dexter. By feeling the hand, Nancy will be able to check that her finger-spelled letters are being correctly interpreted.
Okay, you're ready to touch. Okay.
Hello. I am.
Nancy can tell what she is saying through Dexter. Now, what she doesn't realize is that the system is hooked up to a voice synthesizer.
Fine.
When you fingerspell with the glove, the computer voices for you.
Oh.
Okay. What do you think about using that to talk with hearing people?
I didn't know that. I wasn't aware of it. I mean, when I fingerspell, and then the computer voices for me, I wasn't aware of it. I thought, you know, it came out on a printer or on the braille or something.
No. Voice for you.
Oh, okay, I get it now.
The ultimate goal of the project is to give a deaf-blind, non-vocal person just complete independence. This system allows those same people to speak in their own language, but yet be understood by a hearing person.
Discover decided to put the system to its first field test, a shopping expedition.
I. Cross.
This time, a small portable keyboard controls Dexter.
Dresses.
Nancy's previous shopping trips have always required a human interpreter. She can check the fabric by feel, but some features aren't so obvious.
Does the dress have pockets?
Okay, here we go. Let's try it on.
Thanks to Dexter and the talking glove, Nancy is communicating with a hearing person in her own language for the first time.
Yes.
Yay, okay.
On this trip, Nancy's interpreter, Cindy, came along.
Hi, what a beautiful dress. Wow, this is nice.
Both Dexter and the talking glove are still far too primitive and clumsy to act as Nancy's ears and voice beyond the laboratory. But that day will come.
Nothing's impossible. We had this tremendous project, but within the first 2 weeks, we came up with 5 possible solutions that we really thought could work.
If every engineer developed one useful tool for the handicapped, their lives would be just so much better.
A lot of the technology already exists. It just needs a few capable people to tie a lot of the technology together and to build some really incredible devices that can make a big impact on disabled persons' lives.
The ultimate goal, still very far off, is a robot hand able to compete with the human hand on more equal terms. The Utah hand has 3 fingers and an opposing thumb. A pinky would have made the hand too cumbersome. Its long arm can't move itself. That is done by an industrial robot grasping its wrist. The point of the arm is to deliver power to the hand via tendons running over pulleys to the fingers. The muscles that move the fingers, 32 pneumatically powered pistons, are also in the arm, an idea borrowed from human anatomy. It's strictly an experimental device. The idea is to find out how hard it is for a mechanical hand to do what for a human hand is easy. If the grasp isn't perfect, a task even a 3-year-old finds simple can prove very frustrating. Like the human hand, each finger and thumb has 4 joints, 3 allowing them to bend, 1 for movement side to side. Each of the joints is controlled independently by a pair of tendons. And it's in the precise control of the hand that the really complex problems lie. It's to explore control problems that, across the country at the Massachusetts Institute of Technology, another hand has been built, unlike the Utah hand, with some very unhuman attributes. Mechanically, the MIT hand is much simpler, but it is controlled by a powerful computer that's able to think out for itself how to grasp and move objects. Here, the computer's been told only the shape and the size of the block. The grasps it's using are its own ideas. Hand designer Ken Salisbury.
So here you see a rather unusual grasp being held between 2 fingers, something that would be rather uncomfortable for us. We don't normally hold objects between our 2 fingers like this, but it's perfectly acceptable to the robot in this case. And then we'll see it execute a more familiar human grasp of opposing the thumb to 2 fingers. And one of the features of this planner is that it actually is not only choosing where to grab, but also the stiffnesses at the individual fingers, so that it can hold securely without exerting excessive forces on the object. So it's a rather delicate but secure grasp that we're achieving.
Remember now, the hand has not been told how to move its fingers. The only information it has is the shape and the size of the block. Information one day it will get from its own vision system.
So this is the type of work that puts us maybe a step closer to being able to say to the robot, go grab the object, and it can, quote-unquote, think about what it means to pick up the object and how to hold it in a way so that it won't drop it.
The MIT hand may be smart, but its 3 fingers limit how well it can substitute for the human hand. The Utah hand, built with MIT collaboration, can, by contrast, become a direct mechanical extension of the human hand, and so can be controlled by the human brain. Sensors in a mechanical glove allow the robot hand to mimic the human one. A hand like this could be sent off by itself into places hazardous for humans, a nuclear power plant, say, or undersea, or even in space, and be operated by someone simply watching a television screen. But there's something we can do without even thinking that is way beyond a robot. We can feel objects slipping and sliding between our fingers and so manipulate them with ease. So giving a robot a sense of touch is the next big challenge. These are strain gauges built into a sphere that's like a giant fingertip. Linked to a computer, the gauges allow the sphere to tell just where it is being touched and how hard. The longer line shows the force pushing into the sphere, the shorter line the force sideways. The sphere and the miniaturized version that would become robot fingertips are built by MIT graduate student David Brock.
Now what we're going to use these fingertips for is attached to the robot hand. The fingertips can then determine the locations at which it touches objects, and from that it can determine what the object is and how hard it's grasping it.
A robot hand able to substitute for the real thing on assembly lines or far out in space, or even when someone has lost a hand, is still a long way off. But it already has some skills that are all its own.